Yeah, so turning down the lignite power plants by replacing it with renewables gives us the highest efficiency in CO2 savings. If we would replace a standard oil heating system in a house by a heat pump, we still can save more than 1 kilograms of CO2 per kilowatt hour of electricity. Or if we go to hard coal-fired power plants, it's somewhat less what we save, and then it's getting lower and lower. Yeah? Using the kilowatt hour in a battery electric vehicle instead of a combustion engine brings us still 670 grams of CO2. And if we look, for example, then to, according to the numbers we just have seen, with a fuel cell car here, we have just a saving of 260 grams, and with an eFuel, maybe only 160 grams of CO2 savings. Once again, a little bit more or less. This is not the main thing of this list, but this list tells us if we have a limited resource in electricity, where we should start when we talk about climate protection. And climate protection is CO2 emission reductions. And all these things can be done. Technically, we can do all these things, but if we have such very strong and very challenging pathways in the CO2 reductions as I have shown to you, then it is important to know at least where we can do which savings. It could be necessary in applications to start also right now with maybe within a technology which might have a relatively low efficiency right now, but thinking about steel production, for example. If you build this plant for producing steel, this has typically a lifetime of 40 years. So if you build a new one today, you may like to operate it until 2060 and beyond. Yeah? And if you build it today again with the old technology, then you will remain with the emissions until 2050, 2060, or you have to turn it down, but then it's stranded investment. Yeah? So in such applications, it also can make sense to switch over right now already to hydrogen, even though we have very little hydrogen, and we may use hydrogen even from non-renewable sources, because in the long run, it pays off. Yeah? So everywhere where we have processes which take very long to change things, you have to start maybe, even though the placement on this list might be relatively low. Whereas, for example, for jet fuels, there's no real need to start now, because we can produce artificial jet fuels which are chemically almost completely identical to today's jet fuels. So you don't need any changes in the infrastructure at the airports. You don't need to change the engines and what else. Yeah? So once we have sufficient jet fuel, we can use them right away in the airplanes. So there is no need to change the airplanes already starting many, many years beforehand. Whereas in a car, you cannot simply, combustion engine car is a combustion engine car and will not turn into an electric vehicle after 5 years of operation or something like this. So there, you also have to start somewhat earlier. And such calculations can be done, and I don't want to go too much into these details, just to show you how these things can be calculated, just about carbon content and energy demands and so on. You may have a look into this. I put for 3 of the numbers I put here in the table we have seen before, more details on how to calculate this. But at the end of the day, this all goes down to very fundamental data like weight of materials and energy contents and so on. So these are very basic numbers which hardly can be changed so much. Same here for the vehicle operation, for example. I assumed here a replacement of a car with 5 liters gasoline consumption per 100 kilometer. I assume 15 kilowatt hours electrical power per 100 kilometer, and then you can calculate how much CO2 you save by using electricity instead of the gasoline. Yeah? And if you think the numbers should be different in terms of the gasoline consumption or the electricity, you can change them, no question, and then you will come up with slightly different numbers. But as the efficiencies always multiply, you will see changing one of these parameters somewhat will not change the overall result really dramatically. Yeah? And this is then about the fuel cell car, taking into account some efficiency for the hydrogen production, for the fuel cell system, not the stack on its own, the system in total, efficiency of gas compression and fueling, and so on and so on. Right. Another thing which should be also kept in mind, it's not always the latest technology which can result in best efficiencies. So in Germany, since many years, there is discussion about these power to gas, which means nothing else than what we are talking about, taking electricity to produce hydrogen first and then typically to take CO2 to make methane. Yeah? So and then we have same as natural gas. And this is what is called power to gas. Yeah? And the people were always talking about setting up these electrolyzers and the methanization units and so on. But you can, let me say, generate gas also in a different way. And this is what I would like to show here. Yeah? So we're starting with having some source for electricity, sure. Then if we're going for these classical power to gas, we take the electricity, we bring it into hydrogen generation by means of an electrolyzer. Then we have to do the methanization, so taking the hydrogen and making CH4, methane from it. And finally, we have some gas. So that's relatively easy. And this has some investment cost. So taking a low value for the electrolyzer and the methanization, you at least pay 500 euros per kilowatt these days. Dollars and euros is almost equal, not completely. And we have a certain efficiency, and this efficiency is maybe in the range of 60%. So 60% of the energy we have here as electricity may then be stored chemically in the gas. So this is what we can achieve. But I can save, or I can do this also in a different way, because as I said, at the moment, more than 80% of our heating systems, including the hot water heating, so also in the summertime, there's a significant consumption, are operated by gas and oil. So if I have surplus energy, I also can transfer it via the grid into the normal heating systems, and I add into the heating system, which is based on heat, on oil or gas, I heat just a resistive heater. And then, in case I have surplus energy, remember this is a negative residual load in the grid, I can send a digital signal to the heating system and telling there is surplus of energy. Now, I offer you electricity at a very low price. Because what happens if there's surplus of energy? Either it is sold somewhere to the neighboring countries at almost zero, or you have to switch down wind and PV generators. So the value is low. I give you electricity at a price which is cheaper than oil and gas. Switch off your oil and gas heater as long as we have the surplus, and take the resistive heater. And what do we have from this is, at the end, we have gas or oil. Because gas we haven't burned is still there. And it's obviously the same gas as we have produced beforehand. But the difference is, these additional resistive heater is at significantly below 50 euro per kilowatt. You can buy it. So every manufacturer of these heating systems offers such resistive heaters. And the efficiency is, just taking into account some grid losses, is significantly higher. So at very marginal cost, and with high efficiency, I can have the same effect. I have more gas available than in case I would have do nothing. I'm using this electricity to produce gas, either by really producing it or by avoiding the usage of the gas. And at the end of the day, that's the same. And as long as we have such a high demand of oil and gas in the heating system, before we really go into the production of new gas via this very capital-intensive, high-technology pathway, it makes sense to go other ways beforehand. Maybe not so technology, looks not like high-tech somehow, but requires at least a certain communication infrastructure, digital infrastructure. It requires different prices for electricity. So prices should be different when there is no normal electricity demand or for this surplus use. But this is true for the electrolyzer as well. The electrolyzer will not buy electricity prices at the normal consumer price level because then the hydrogen cannot be paid for at all. Right, so this is about efficiency and CO2 reduction, and this is what we always should keep in mind as one of the factors. Again, it's one of the factors, and it's only part of the truth, no question. We also have investments in the production of components. Everybody knows there's quite a bit of energy which is needed to produce a battery, for example, in the production process. Has to be taken into account, no question. But by the way, and this is what most people overlook, is if you build a fuel cell car with a 700 bars pressure tank, to produce these pressure tanks consumes almost the same amount of energy as a battery. Because this is a high temperature process, these are these carbon composite materials. So the fuel cell car has not less energy in the production than the battery electric vehicles. But both have more than the conventional ones, also no question. And on the other hand, also, I did all these calculations with only the direct emissions coming from using fuels. But depending on the studies you read, at least another 40% of the emissions you have directly in the exhaust of a car comes in the downstream, from the downstream process, from the mining of oil and gas, the production, the refineries, transport, and so on. So there comes additional emissions on top. And again, on the other hand, also wind and PV are not totally CO2 free. As long as we have not a CO2 free production world, the production of wind turbines and PV also costs CO2 emissions. And they're also not taken in these simple calculations into account. So things are in total even more complex, but most of the things you can judge relatively easily when doing first order approximations. So now let us look at what we achieved so far in the passenger vehicle sector. As mentioned already, there's a ban of passenger cars with combustion engines latest until 2035. We don't expect that this is for Europe really a problem because the vast majority of the car manufacturers in Europe have announced to switch over to 100% electric fleets between 2025 and 2032 already anyway. So politics have lots of discussion about these 2035 companies have already made decisions which going well beyond this. And there are different reasons for this. First of all, batteries getting cheaper, the cars getting cheaper, and everybody knows the electric vehicle drives very well. But it is also a matter of economic efficiency in the companies because it is very difficult to develop different technologies in parallel. So today's car manufacturer like Volkswagen or Mercedes, they have maybe 5,000 engineers in combustion engine engineering and another 3,000 in gearbox engineering. If you want to continue with the conventional cars, you still need them. But at the same point of time, you need the same amount of people for batteries, power electronics, and electric vehicles. You simply cannot afford this. And this is also the reason why the car manufacturers decided much earlier than politics, now, no, we are going for the battery electric vehicles. We will not go for the fuel cell cars because we simply can't do both at a time. And fuel cell cars anyway will take more time, and therefore we are quitting this. The same is with eFuels. So this is always something you should take into account. From an academic point of view, it might make sense to keep different options open. But at the end of the day, if you have to develop all of them, then you get really into trouble. So when looking into the different types of cars, you all know this. We have the gasoline combustion engine cars here, and then we have hybrid electric vehicles, hybrid electric vehicles, which just have a certain support from the battery and electronics, but not getting energy from the grid. Then we have the plug-in hybrids. They are quite popular in Europe until now, with almost 50% market share, but now with a reducing share from now onwards, having a small battery charged from the grid for distances maybe up to 50, 70 kilometers or something like this, but for the long distances still having the combustion engine, and then changing over to the full electric vehicle with the batteries here. And the driving ranges today, driving ranges are somewhere in the range of 300 to 500 or 600 kilometers with today's batteries. Yes, please. Maybe we have to bring you a microphone because otherwise the digital audience can't hear you. Perfect. Thank you.
Okay. I just want to comment. I'm enjoying your presentation today. The question I have is about for electric vehicle battery, specific in Germany where the weather is cold. Where does that fit in with the existing batteries that have some charging issues or discharge issue in a cold weather? And I comment that because I think, you know, I'm from the US, and I think in the U.S., this is an overlooked phenomenon where people are not realizing that the batteries are affected by cold weather. Yeah. And I'm aware of some efforts, I think from Germany, with alternative batteries to lithium batteries that can be used in cold weather and not have that problem. But my understanding is that's still in the research. So how is Germany handling that? How are consumers handling when there's a cold winter and certain population has an electric vehicle?
Yeah, so thank you very much for the question. Indeed, first of all, a cold winter in Germany probably is much warmer than a cold winter in the US. So if we talk about in Germany about a cold winter, it's minus 10 to minus 15, but not more than this degree centigrade. Yeah. So, and I know that there are periods of time in the North America, sorry, where temperatures are even significantly lower. Yeah. So the good news, at least, is we have 1.2 million electric vehicles on the roads by the end of 2021. And we had a cold winter in some weeks this year, and these cars were all running, first of all. Yeah? So this is the easy part of the answer. But on the other hand, you're totally right. The batteries have a problem. Lithium-ion batteries have a problem with charging at low temperatures, not with driving. In driving, the performance goes down somewhat, but this doesn't matter too much because when you start driving, the batteries are large, so you can start driving, and while you drive, the temperature increases of the battery due to the losses, and therefore you will get wherever you want. So the driving is not the problem. The charging, just as you mentioned, is the problem. Yeah? And indeed, so technically speaking, what happens is if you charge a battery at a cold temperature too fast, then lithium is not intercalating into the graphite. It is deposited as metallic lithium on the surface, and this goes into heavy reactions with the electrolytes and therefore ages the battery significantly faster. Yeah? We just discussed it in the lecture the last 3 days. I can show you data from test benches where we charged the batteries at minus 10 degrees C in 1 hour, and after 3 cycles, the battery was at end of lifetime. Yeah? So there is a problem, but the good news is if we have here the temperature and here the current rate at which you can charge the battery. Yeah? there is so somehow this looks like this. Yeah? So there is always an area of currents, or for a certain temperature, there are currents below this curve which are acceptable without getting into these problems. And if you go beyond, then you get into trouble. Yeah? So if you want to do really a fast charging, yeah? So in Europe we are now going for 350 kilowatt chargers for the upper class cars. This gives you about 100 kilometers of mileage in 3 minutes in charging. But for this, you need temperatures in the battery at maybe about 35 degrees C and somewhat like this. Yeah? But even at the low temperature, there's always, for each temperature, there is a current rate at which you can charge the battery. And this is a good news, because if you can start charging the battery, then due to the high internal resistance, the battery will warm up anyway. So with the continuing the charging process, you're getting more and more into the warmer region, and you can charge faster. When you're on a trip anyway, on a highway trip, and you want to recharge after 2 or 3 hours of charging, then it doesn't matter anyway, because then the battery has heated up until here. That's not an issue. But if you have your car in your garage or wherever, or outside on the road, then you have to start with a very low current rate. So, and the big thing is the battery management systems must know these values. Unfortunately, they are changing with the age and the state of charge and so on. And the chargers must be able to take this information. But the modern cars and the modern chargers do have this. Yeah? For sure, they typically are significantly below this critical line. Yeah? But this is, just as you mentioned, this is part of our research. For example, we're working with the car manufacturers of model-based strategies to predict really precisely to get very close to this value in the car with the charging, to be as fast as possible, but to avoid under any case to get up there. So therefore, this is it is a challenge, but it is nothing which stops it's no showstopper. Yeah? But it requires, as you said, this, we call this lithium plating. This is one of our major research fields, understanding this better and finding these diagnostic tools, either model-based or cloud computing or whatever, to avoid these things. But yeah, it works. And we don't have other battery technologies really in place for the automotive sector at the moment. Right, so finally then, a fuel cell car, as you know, also contains a battery. Yeah? So from a battery researcher's point of view, you have also here the fuel cell and a battery in addition for the acceleration, but for sure also the fuels in there. So once again, here are just these numbers of CO2 savings. By the way, if we convert trucks to battery-driven trucks, the savings are significantly less compared with passenger cars. And the simple reason is that truck engines, when they go on highways, have a significantly higher efficiency. A truck engine at constant speed on a highway achieves efficiencies in the range of 42%, whereas the average efficiency of combustion engines in the overall driving, not on highway only, is more than 25–27%. Therefore, it means the savings of CO2 in a truck is less, because it emits per kilowatt hour of necessary energy for moving the truck. It uses less gasoline or diesel. But what has changed in the automotive industry, especially, that we are now in the phase where all the new electric vehicles are purpose designed. In the first generation of electric vehicles were converted cars. For example, here's an example from Volkswagen's e-Golf. And this was a shape of the battery in this e-Golf, because they removed for sure the combustion engine and the gearbox and so on, and in the white space they put the batteries. Very complex design, very difficult to manufacture and so on. even from the battery's point of view, you have different temperatures in the different regions of the battery pack and so on. The new designs, and they look with Tesla started with this, but the car manufacturers all followed, is this type of concept. You have the battery and the grounds of the car in most of the cases, and then you have the axis with power electronics and motors. Sometimes you have motors on both axes, sometimes on the wheels. This doesn't matter. But this platform, for example, which is called the modular electric building block at Volkswagen, but as I said, other manufacturers have similar things, is used as a basis, and based on this they build probably meanwhile 2-3 dozens of different cars, different brands. Audis, there are Audis based on this platform, Porsche, Seat, Skoda, even Ford. Ford has purchased this platform as well. And the cars are very different, different size and so on, but it's always the same platform they use. And you can see this is much more simplified, and this is very significant in cost reduction. And we have to be aware, companies like, or a company like Tesla, no, it's the only one. Tesla is already earning a lot of money per car. Tesla has a rough earning of almost $10,000 per vehicle they sell. That's the only ones. All the others have significantly smaller earnings, but Tesla can earn also significant amounts of money. So you see, you can put whatever chassis you would like to have on these platforms, and this is a big advantage. When looking to the international markets, we can see that the number of battery electric vehicles has increased dramatically. So in 2021, there was something like 450 different models available from the car manufacturers worldwide. Roughly 1/3 of them are plug-in hybrids. These are the black ones here, the blue ones here, and the light blue, these are the full electric models. And you can see the driving range of the plug-in hybrids is more like 50 kilometers, not too much change over time, whereas the driving range, the average driving range of the new electric vehicles increased from something like 260 in 2015 to an average of 420 in 2021. So this is, first of all, just what is the models there. This is just, again, the driving range here. You see there's a significant improvement in the last years. But also the markets started really to increase. These are sales numbers, the electric vehicle markets worldwide, so the millions of new cars sold to the markets, and we can see in 2021 this was something like 6.5 million electric vehicles which have been sold to the world market, resulting in a market share of about 8.5% to 9%. So this is already out of what is called a niche market. So this is a significant market. You should keep in mind the largest car manufacturers in the world, like Toyota and Volkswagen, they roughly produce 10 million cars a year in total. The electric vehicle market itself is 6.5 million. So this is almost the size of the largest car manufacturers, at least somehow. And we can see also the cells into the different regions, but I have other data on this here on this slide. Here we can see now the integrated number, so the cumulated number of cars. So the total car stock was something like 16 million in 2021. And we can see half of them is in China. And the rest of the world shares the rest of the cars. And thereof, the majority, again, is in Europe. So China and Europe are by far the most important electric vehicle market, at least until 2021. 2022, this changed a little bit because the European market did not grow too much in 2022, just because we had shortcomings with components, electric components and also batteries. So the market growth was not that dramatic. These are the number of registered vehicles in Germany. You can see at the end of 2021, it was a total of 1.2 million, and almost perfectly half of them were plug-in hybrids, and the other half was full electric vehicles. This will now change. First of all, the car manufacturers are not developing really new models with plug-in hybrids, and also the government stopped the subsidies by the end of 2022 for plug-in hybrids. They're still paying subsidies for full electric vehicles, but not for plug-in hybrids anymore. We may discuss this, but at the end of the day, when we want to come down with the emissions, there's more or less no other choice. So this market is growing at least quite well. For Germany, it was about in the range of 20 to 25% of the overall market in 2019, 2021. But the stock, and this is important, even though you have a share of 20 or more percent for the newly sold cars, it is only 2.6% of the overall stock. So it's a small percentage of the whole fleet, which is about 45 to 48 million in Germany. From the batteries point of view, we are also interested to see how much capacity of batteries are in these cars. And I would like to put emphasis here only on the left-hand side figure. This is the battery capacity installed in these vehicles, taking into account the size and so on. Everything is taken into account. So this is really counting of the different models with their specific battery size. And we can see that the overall capacity in battery vehicles was, by the end of 2021, something like 40 gigawatt hours of battery capacity. First of all, this may not mean too much to you what 40 gigawatt hours means, but it might become interesting if I tell you that the total capacity of all pumped hydropower stations in Germany, so this is a technology which is used to level the power generation in the grid. All these pumped hydropower stations which were built in the last 100 years, step by step, equals 40 gigawatt hours. So just 2.6% of the vehicle fleet already have a storage capacity which equals all the pumped hydropower stations we have in Germany. And this is one of the reasons why we are absolutely convinced that the storage capacity of these cars, which is standing around 22 to 23 hours on average per day. The cars only drive 1 to 2 hours a day, not more than this. That we have to make use of this capacity for balancing the grid, especially in the increasing share of renewables. Because it's a huge capacity and even larger power which can be applied to the grid or taken from the grid depending on these fluctuations. It is also worth mentioning that the automotive market is by far dominating this market of modern battery technologies. If we just take into account here the mobility, plug-in and battery electric vehicles, but looking in addition to large-scale stationary storage, industrial storage and home storage systems, we can see that the stationary batteries make up about 10% compared with the overall market. And predictions also for the United States market look pretty much the same. So this is one of the reasons why technology like lithium-ion batteries, which really is the main technology, first of all in consumer products and then in the automotive sector, have these economy of scale advantages, and a technology which is just developed purely for the stationary sector has much more difficulties in reducing the prices by economy of scale to really get into these markets. And this will most probably not significantly change. Looking to the different countries, we can see also some interesting things. China in 2021 was a very strong increase in the market, whereas in the 3 years before, the market more or less stagnated. This was due to the change in the governmental policies. They changed over from subsidies to a point system for the manufacturers. So now the manufacturers are forced to sell a certain amount of their cars with an increasing share. And this took a while until this really became effective. But you can see in 2021, this was almost a tripling of the market. We see also a steadily strong increase in Europe. United States are well behind this, and the rest of the world is relatively small. It's also especially interesting looking to countries like Japan and Korea. As you can see here, at least the belief into this market is not too high. They are selling these cars all over the world, but the national markets in China and Korea are small compared with European markets, for example. And that the German market is largest compared, much significantly higher compared with France and United Kingdom is also just simply a matter of population. So Germany has a significantly higher population than France or Great Britain. So per capita, the differences are not that high. A little bit higher in Germany, but not so important. Who's selling these cars in 2021? Tesla was the market leader, Volkswagen behind BYD, GM, and Stellantis, a French, Italian car company. But these numbers are changing rapidly, especially the Chinese car manufacturers increasing their outputs really dramatically, whereas other traditional car manufacturers are, some of them have more or less steady state. Tesla is increasing, no question, but especially the Chinese also come now to European markets, United States market, and so on. Looking on the other hand to the fuel cell car markets. So this was the numbers for the electric vehicle market. Please remember, it was 16 million in total stock into the end of 2021. These are the numbers. These are the numbers for the fuel cell vehicles, and you can see. So these are here the light-duty vehicles, the passenger light-duty vehicles, and the total number of fuel cell cars on Europe in the world in total. And by the end of 2021 was about 42,000. So 16 million battery electric vehicles, 42,000 hydrogen cars. And here you can see why Korea and Japan probably are somewhat lower in the electric vehicles, because they believe more in the fuel cell cars. You can see the almost half of the world's stock in fuel cell cars, but which is still less than 20,000, is in Korea, and Japan has also a quite significant share. Germany has some, United States some more. In addition, we have some buses and we have some trucks, but both is equaling maybe 5,000, and the vast majority is again here in China. All the other countries is almost marginal by the end of 2021. So the battery electric things are really mature technology, large scale. The fuel cell cars are extremely niche markets until now. It is also interesting to look at these numbers here, because this compares on the one hand stock in fuel cell cars. This is the outer circle here. This represents these vehicles, Korea with the largest share, United States, China, Japan, and also Germany here. And the inner circle is, interestingly, this shows you the share of hydrogen filling stations. So you can see, especially if you look to Germany, only 3% of the worldwide fuel cell cars, but 13% of the worldwide stock in fuels and filling stations. And this is very much political driven, because there are still lots of politicians who think hydrogen should be the future, and they give lots of subsidies for putting in these filling stations, but nobody buys and builds the fuel cell cars, because the industry in Europe still, since a while, has decided not to go into this. So that's sometimes interesting to see, and this is a nice diagram which shows what happens if the government thinks a certain technology is good and what the market does. And finally, I would like to put the emphasis on something else, which is true for all of these different technologies, but especially when we changed over now towards to the battery electric vehicles and so on, everybody was talking about how to increase the size of the battery and decrease the price of the battery, so to get longer driving ranges and so on. But to be very clear, the usage of a battery-driven device always has two sides. The one is the power supply, but the other one is efficiency in power consumption. If you look to your smartphone, for example, at the large smartphone manufacturers, you have huge departments working on the improvement of batteries. But at the same point of time, you have departments which have more or less the same size working on the energy efficiency. So with lots of different measures, they reduce the energy consumption. And this is where we just have started in the automotive industry. And this is an example. It is for sure a study. So this is a single car, handmade, nevertheless. This is a Mercedes. The dimensions are pretty much like Mercedes S-Class. So this is a luxury car of Mercedes. And here in this car, they try to put in place everything they could do to reduce energy consumption. And today, on average, electric vehicles on German roads consume about 19.5 kilowatt hours of electricity per 100 kilometer. Engineers here were able to reduce the power consumption while driving on normal roads, including highway, to something like 8.6 kilowatt hours per 100 kilometer. So this car with a battery, with a standard battery of the S-Class, with about 100 kilowatt hours, really drove 1,200 kilometers with one battery charge. From Munich to London or to France, southern part of France and so on. And I think, for sure, as I said, this is a prototype and an experimental car. Not everything you will see here will become reality in the serious cars, no question. But it shows a potential. There's a potential of reducing the electricity consumption dramatically by reducing the air drag, for example. So you have total degrees of freedom here in the front part because you don't need the cooler anymore. The efficiency of the overall drivetrain is so high that you don't need a cooler anymore. You would need a cooler for a fuel cell system, by the way, because there lots of heat have to be dissipated at relatively low temperatures. They look for the wheels and the resistances and so on. But I just want to put emphasis on this. When we talk about all this change in the energy system, we should look only to the supply side. We have to look very intensively also to the consumer side. And the consumer side here is efficiency especially, and it will become much easier for us if we can reduce the energy consumption to do this switch over rather than we stay with where we are. But all of this means the worldwide demand in battery increases dramatically, and dramatically fast. So we expect already in 2025 to 2027 somewhere a demand for vehicle batteries in the order of 1,000 gigawatt hours per year. This is huge. So when Tesla announced 2013 the first battery gigafactory of the world, this was at a capacity of about 35 gigawatt hours. So what we need in 2025 or maybe 2026 is the output of 30 of these gigafactories worldwide, and doubling at least doubling towards 2030. So just Volkswagen wants to build 6 power plants with 40 gigawatt hours each just for the European market until 2030. And with this I would like to go a little bit into some state of the art of batteries. We already discussed one of these things regarding the cold temperature operation. Why is the lithium-ion battery so successful? It really has a significantly higher energy density, as you can see here from the Ragone diagram. with these specific gravimetric energy density, so watt-hours per kilogram on the x-axis, the power rating here on the y-axis, and you can see different types of lithium-ion batteries, which is a huge family of different technologies, is superior to all the other technologies we have available these days. And the only technology which we expect to come into the automotive market beside lithium-based batteries in the coming years are sodium-based batteries. But they are pretty similar to these lithium batteries. They have the same working principle, the same cell design. We're quite sure you can use the same production lines, but the performance will be less. But the prices could be lower because sodium is significantly cheaper than lithium, so there is a good chance to do so. To catch up with all these increase in the automotive industry, there are lots of initiatives. These are initiatives for Europe for building production sites for batteries, for lithium-ion batteries, because today almost all manufacturers are Asian companies. The Asian companies have, meanwhile, manufacturing sites in North America and in Europe, but we need significantly more, and therefore also governments try to support this drastically. And here you can see forecasts of the market. This is now everything, all different types of stationary and vehicle markets you see here in 2025, including the stationary market, somewhat more than 1,000 gigawatt hours per year, and towards 2030 the expectations are close to 3,000, and through 2035 more than 4,500 gigawatt hours per year. So this is for sure a huge changeover, but you should be aware, in a full electric vehicle, about 1/3 of the value is the battery. This means, simply speaking, from the overall worldwide automotive industry in the future, 1/3 of everything, of the stuff, of the factories, of the supply chains, is just battery. 1/3. So this is really very significant. And 90% goes to mobility applications, as you can see from this prediction as well. Internally, such a battery looks like this. So you have two electrodes, cathode and anode. You have current collectors with aluminum and copper inside, and then the graphite on the copper here, a separator in between to avoid short circuits. And here you have lithium metal oxides of different mixtures. And the problem we just discussed earlier appears during charging when the lithium ions move from the cathode towards the anode. And the anode has a potential which is close to zero regarding a reference electrode. And if it's too cold and you charge too fast, the potential may go below the 0-volt line, and then it is not diffusing into the crystals anymore, what it should for long lifetimes and safety, but it is depositing on the surface of these crystals. That is this lithium plating. This is exactly the effect we have discussed. So this is indeed a significant problem. And it's very difficult to predict if a certain battery has, or where I showed this line here. And the problem is it is very different for all batteries, because the materials which are used, even though they use all graphite today, sometimes mixed with silicon, but even if it's called graphite, I just wanted to show you these 5 pictures here. These are laser microscopic pictures. The scale here, this is 100 millimeters here. And you can see, and all are done with the same device, same magnification and so on, same preparation. But on the first glance, you can see the structure of these materials is very different. Some seem to have relatively large crystals, others seem to have quite low crystals. So the performance is very different. So the smaller the crystals are, the higher the charging currents can be, for example. So smaller crystals are good for high performance and for fast charging, but on the same point in time, at the same point of time, they are also prone to significantly faster aging. because on the surface area of the crystals we have the main aging process independent from cold temperatures or something like this. I just want to show that even though from the nameplate it seems you have similar materials, they are not at all similar. Yeah? Manufacturer of carbons typically sells 2,000 different modifications, all a carbon, yeah? But 2,000 different products. Yeah? And therefore, it may become clear how difficult this is. This is a view even deeper. This is where we really have to look at to understand all these processes. Beside the active materials, we have also binders, which act somehow like a glue between the particles. We have some other carbon inside for better conductivity here. We have the graphite itself. We have the pores for the electrolytes and so on. But if you really want to do research on this these days, you have to look on this level to understand how fast charging, for example, or acceleration or high temperatures affect these different elements of such a material. And just from a schematic point of view, before we go to lunch, this is how such a lithium-ion battery generally works. We have the graphite anode, we have the cathodes with the lithium metal oxide, and the lithium battery is a so-called intercalation battery. This means the crystal structure of the graphite and of the cathode remain untouched during the cycling of the battery. The only thing that happens is that during discharging, lithium ions are released from the anode and traveling into the cathode, and they are going into this like into a sponge. Yeah? So they're going into these intercrystal spaces here, and while the ions going through the electrolyte from one electrode to the others, we can make use of the electrons which go through the outer circle. And during charging, things are just turning around. Now the ions are moved from the cathode to the anode, and as I said, if we are doing this too fast, then the intercalation into the graphite will not take place. This is like a traffic jam. Yeah? So if you send too many lithium ions at a time, which cannot diffuse into this either because it's already charged, or it's cold. When it's cold, then the diffusion into the solid state material is very slow, and then you become here on the surface area a traffic jam, which is called lithium plating and accelerated aging. Yeah? So this is how this is. And I think before we are looking a little bit more into these battery things, it's now 12 o'clock, and I think a good time for going for lunch, but not before you may have one or the other questions